Hello there, math fans. Going to continue discussing circular motion. Watch my previous videos about general information about circular motion. I also made one about a merry-go-round. But this one's going to be about spirographs. This video in particular is dedicated to my nieces and nephews. In particular, my niece Maya, who I bought a spirograph kit for, and she probably was like, great, this is really what I wanted for Christmas. This terrible art set. But I was thinking about this thing that I like, and I wanted to explain why I liked it. But also for my niece Anna, who we just did some spirographs when she was visiting. It was lovely seeing her. And for my niece Jude, who I've already spoken about in other videos, and for anybody who wants to do some art, this is an interesting, fun little thing that always was kind of amazing to me at how simple you could make it. But it's just an opportunity for me to discuss circular motion in yet another way. Again, this is a topic that often confuses my students. They're confused by different pieces, and I thought by showing some interesting things you can do with circular motion, maybe it would take some of the mystery away, or at least would make it worthwhile to learn. Before I start, I want to explain what a spirograph is. I really didn't know much about these growing up, but I encountered them more as my kids were doing things. So I'm going to switch over to show you what a spirograph looks like. Okay, here we go. So a spirograph looks like this. I have the world's cheapest kit. I realized I probably should purchase another one, but so I can do more stuff like this. But typically it has gears on the inside or outside to just help you do it, and then a bunch of gears you can put in there. And the one pro tip, based off of me sort of making these videos for my nieces and nephews, is it doesn't hurt to tape this down in some way so it doesn't move very much. If you're working on the inside, then you pick a gear, whichever one you want, and you pick a hole, whichever one you want. That's, you get some variation here. And then you try to keep it up against the side. I should be using like a pencil or something sharp. You got to push against the side and just keep going. And I realize now I should have grabbed a pencil. But as you keep going, you realize you make these pretty interesting shapes. It's pleasing. So there you go. I didn't do it perfectly, but there's one example. You can keep going and it kind of fills in, but you can see these interesting shapes you get. If you pick it up, bad that I taped it, you can do another one, maybe with a different size. You can see what happens when you pick a hole closer to the middle, and you can just play the game again. Sometimes with the smaller gears on the inside, it's easier to do it. And they're pretty awesome. So we did one like this, and I have a picture of it in my OneNote, and we're going to work from that. And I'm going to show you how to actually draw this on a grapher, and then I'm going to share that with you in case you want to play around with it. I'm going to share my Desmos file, and so that you can make these on your computer as well and play around with circular motion. I thought before I did any more, I would do one more. This is kind of for my nieces, a little hack. And I searched online. It's actually a place in Vancouver. I think it was Vancouver, BC, where someone makes specialized versions of this. But you can also do on the outer edge. Now, unfortunately, the kit I came with did not have gears on the outer edge. I did notice in order to do this, you really need to put a piece of tape down because your hand gets in the way otherwise. So I put a piece of tape on this bigger gear. And I don't know what's going to happen, so this is a bit experimental. But I'm going to pick a dot here somewhere, and I'm going to run around the outer edge. This might work terribly because I have this thing taped down, but I'll try. And you can play this same game. Turns out sometimes shapes like this have important applications in math. There's this thing called the cycloid, which you get basically by doing this same thing but over a straight surface. So you get these surprising shapes. And I encourage anyone watching this video to try to make some. You can send me some shapes. Oh no, I messed it up. In art, we mess up. We just keep going. So I find that this one's harder to draw, but we'll make some pictures of this. I need to do lots of loops. I don't know what's going to happen. So I think I'm going to stop there since my art isn't turning out very well on that and switch to the math. But, you know, play around with this. It's better if you have a pencil. It's better if you fix it to this. So there are some challenges to getting it to work. If you're doing the one that's inside, it actually works out pretty good. You know, you pick one. You can do it fairly quickly, which is cool. But the outside, you know, is a little harder. So it's surprising how quickly I can make an image like that. Okay, so let's switch. Okay, now coming back to the problem. This is the spirograph I did with my niece this weekend. And I measured a couple things using a ruler. I measured from here to the edge of the spirograph equipment was 2.9 centimeters. And I measured that the gear I used was 1.5 centimeters. And that the circle I used was 0.5 centimeters. And I set everything up nicely so that it looked like this, so that my analysis was fairly nice. And then I have my little dot right here. And then I went around this thing. So ultimately I realized there were a couple things. So one is I need to generalize this formula slightly. If you have a circle that's not centered at the origin, but it has some center, let's call it XC, YC, and you're rotating around that. Turns out it's the same formula, you just have to shift it. Meaning the formula for circular motion here is XC, YC plus R cosine of theta plus R sine of theta. And we're going to need that in a second because one of our circles is not centered at the origin. And then I was thinking about this, there was a couple key observations. One was I can describe the center there. That's a circular motion problem like we've already done. Meaning if I remove everything else from this story, the center here of this circle is just going to move around like this. It's going to start at this point, which we'd have to think about because the radius is 1.5, so it's going to be 1.5 from here, which means this is going to be 1.4. So anyways, it's going to start at R, big R. Let's call big R. Here's what I'm going to label. Big R is 2.9. And let's have A be the radius of this other one, 1.5. In my notes I used little r, but I realized when I went to, I'm going to show you some visuals in a second. And when I went to use the visuals, it doesn't like me to use little r. So I'm going to use the same thing as my visuals. And then R minus A, this 1.4, is this actual radius. Okay, so if I'm describing the center, this moving center of this other circle, then I can use the same formula. It's circular motion. It's R minus A times cosine, and I'm going to call this theta 1, and that'll make sense in just a second. I'm going to call this sine of theta 1. Okay, so let's kind of step back. That's circular motion. Now I've described the center. And after a certain amount of time, you're going to have this angle theta 1. Now there's a couple little observations. One is that the outer edge of this is what we call arc length, and it's always the radius times the angle as long as you're in radians. Watch my previous video on circular motion if you want to know why that's the case. But there's also the angle of this other circle. So then we have a new job, which is to basically plug this in here. Plug this in here. That's the center of my other circle. My other circle is actually rotating this way. You have to go back and look at your spirograph to see that. So it's clockwise. So there's a little adjustment for that. And it turns out that you need to say the angle's going the other way. And there's several little things, but cosine of negative theta and cosine of theta are the same thing, whereas these are opposite, meaning this is negative sine of theta. Let's call this theta 2, which is the angle the little circle makes. And this was in my notes as I was thinking about this the last week or so. I realized there's one main problem I had to solve, which is what happens to this little circle? How does the angle it change relate to the angle changed by the other circle? And so I realized, well, whatever the angle change was from here to here, I actually thought in terms of circumference, that the circumference of the big circle is this, and the circumference of the small circle is this, which got me thinking that somehow the ratio r over a might come into play. But then I wanted to make it precise. So however much, if you have this other circle that's rotated, we can play the same game, which is how far around this circle have we gone? And it may be more than one loop, but the distance you've gone is always going to be a times whatever that angle is, by the same reasoning. And so the conclusion from that is the following, is that those distances, the distance you've traveled around the small circle and the distance you've traveled around the big circle are the same. And so a times theta 2 is r times theta 1. And that's probably the trickiest part. It took, like I said, it took me a couple of days to realize how to say that simply, and I'm sure I didn't accomplish that. But theta 2 is r divided by a times theta 1. So then we got it all in terms of one thing. So we can say x is equal to r minus a. Maybe I'll replace this with the actual numbers. So in our example, r minus a is 1.4. That was how far from here to the middle of that gear. And then it's going to be cosine of theta. I'll just say that's theta 1. Plus the radius here, this 0.5. That's how far we are from the center of that circle. Cosine. And then this is going to be r over a theta. And then y is going to be 1.4 sine of theta. And then this one's going to be minus, because it's going clockwise, 0.5. That was that thing I was talking about. But sine. And that's what I wrote in my notes as I was thinking about this a couple days ago. There's your spirograph formula. Now in general, this number right here is going to be r minus a. And this number here is going to be how far you are from the center. Big R being the radius of the big circle, a being the radius of the smaller inner circle, and 0.2 being the distance from the center of that small circle to the dot you chose. And this will work. Now, you can replace theta by t if you want, or you can adjust it to be 2 pi over the frequency t. Frequency being how long it takes to do one rotation. Okay. The rest of this, I just want to show you some visuals. So now we're going to switch over to this. So here's this exact problem, and I'll share this with you so you can see it. I have all the radii as given in the problem. Let me make sure I have them right. A is 1.5. R was 2.9. D was 0.5. That was how far I was from that center. And I set it up so that you could tweak it if you want. I'm going to animate this very slowly, and as I animate, I'm going to draw what the pen would draw. Let's start drawing. And that purple circle is turning as you do it. And you get a shape like this. And all that was is basically two versions of circular motion. One circular motion described the center of that purple circle. The other one described the actual motion. Now, if I increase this and go much farther, here's what it looks like. If I move it along, get that beautiful shape. So there you go. You can tweak the pieces. I'll share this in the comments, and you can tweak those as much as you like. Just for fun, I didn't really prepare this very much, but I thought, what if I go on the outer edge? So I quickly made those. Turns out there's very little that changes in the derivation. You're just, instead of r minus a, it's r plus a. So I have an example here. Let's start on the outer edge. Let's pick a little dot, and let's send it in motion. And it's just kind of fun to watch. I mean, you could make these graphs yourself and just watch them. Let's speed up a little bit. This is the graph I was trying to draw, but I was having trouble being accurate with it. But now I can do it much more swiftly. And anticipate what picture I'm going to get. So I thought an interesting fact about this is if you wanted to make a certain picture, you now could experiment on the computer first. And then once you got something you really liked, then you could set up your spirograph however you want to generate that picture. Oh, that's nice. Now, some numbers may not make sense in this, but you can, like, what if the distance from my inner circle was bigger? What if I change one of my radius? And sometimes when the numbers get really big, your picture starts to get not so great. But I find that pretty darn fun. So here you can play spirographs all day, however you want. Again, you may have to increase the T to get a more accurate picture. But there's a bunch of spirographs. Hope you found that interesting. I have many other applications of this in mind. And if you search for spirographs, you can find a lot more things like this that people have done. All right, hope you found that interesting.